Hi everyone, welcome back to Neuroscience for Non-Majors. This is going to be an optional bonus lecture and it's going to have no effect on your grade, but if you're interested you can watch it. But I hope you had a great long weekend and were able to relax on your extra day off. And quick thing about office hours, if you saw my Canvas announcements, you'll know that at office hours, I will have a presentation prepared for you no matter what that will address your areas of confusion that you filled out in your exit surveys at the end of each class. And if nobody shows up to office hours, I'll still record and post that review presentation video on Canvas so that you'll get your areas of confusion addressed. Okay, so this is going to be an optional bonus lecture. Let me share my screen. I think it's loaded. Okay, yeah. So this is going to be an optional bonus lecture that you might enjoy if you want to delve a bit deeper into how voltage-activated ion channels and ion flow work in neurons. This will not count towards your grade in any way, shape, or form, and you're not required to watch this or to know any of the things covered in this lecture for your grade. This is purely for your interest. And I learned all of this material in this that I'm going to tell you in this lecture from my independent study in the fall 2019 semester, and of course I'll reference that at the end. So here we'll be learning more on voltage-activated ion channels, some stuff on current and conductance, and then we'll end by a fun exercise estimating the number of ions that flow through the membrane during an action potential. If you remember from our previous lecture, voltage-activated ion channels are selectively permeable channel proteins in the membrane of a neuron that open or close in response to changes in the voltage across the membrane and let ions flow through. Two super important voltage-activated ion channels for an action potential are voltage-activated sodium channels and voltage-activated potassium channels. What we learned in the last lecture was that the voltage-activated sodium channel can open or close in response to voltage, but it has an additional mechanism to make it more effective, the plug. When the cell is at rest, the voltage-activated sodium channel is both closed and the plug is not blocking the channel. When the cell is in the rising phase of the action potential, the channel is open and still unplugged, so ions can flow through. When the cell is at the peak and falling phase of the action potential, the channel is still open, but is blocked by the plug, so ions are unable to flow through anymore. During the refractory period, the channel is closed and it's also plugged. In reality, though, even at resting potentials, not all of the voltage-activated channels are actually going to be like in that specific state of like closed and unplugged. But most of them are, and it's this fraction of channels that are in a specific state that determines what part of the action potential will be at. Voltage-activated sodium channel states at any given time can be described by the following formula. The state of the plug can be described by a variable h, and the state of the channel can be described by a variable m, such that the conductance, which I'll describe in a moment what conductance is, but the conductance of the channel is equal to the maximum conductance of the channel during the course of an action potential, multiplied by m cubed and multiplied by h. Conductance is the reciprocal of resistance, and it's measured in units of Siemens. The more conductance there is, the more easily current, here sodium ion flow, is able to pass through something. When m equals 0 in this equation, it means that all the voltage-activated sodium channels are closed. When m equals 1, it means they're all open. When h equals 0, it means all of the channels are plugged, and when h equals 1, it means that all of the channels are unplugged. This is not a binary thing though, because when H equals 0.5, it means that half of the voltage activated sodium channels are plugged, while the other half are unplugged. If M equals 0.5, it means that the number of open sodium channels is going to be M cubed, or 12.5% of those channels. The voltage-activated sodium channels can only pass current when they are both open and unplugged. To find what fraction of the voltage-activated sodium channels can pass current, we would need to multiply M cubed with H. We also talked about voltage-activated potassium channels that open mainly at the peak of the action potential to drive the action potential into falling phase by expelling potassium ions from the cell. These channels only have one variable since they don't have a plug, and their conductance can be described by this equation. The variable n describes whether the channel is open or closed, where if n equals 0, then all are closed, and if n equals 1, all are open. To find what fraction of the voltage-activated potassium channels can pass current, we find n to the 4th power. Ohm's law is this V equals IR thing that you see here. And according to Ohm's law, voltage is equal to the current multiplied by the resistance. And resistance is the reciprocal of conductance. So G, conductance, is equal to 1 over resistance. So voltage is equal then to the current divided by the conductance. So if we're trying to find the current, then we multiply the voltage with the conductance. So how can we find the total current moving across the membrane at any point? And again, here current is describing the ion flow. Now that we know the equations for conductance of our important ions, we can solve for the total current moving across the membrane. From our last lecture, remember how we said driving force of an ion population was defined as the voltage across the membrane minus the equilibrium potential of the particular ion? So it's voltage minus voltage, meaning it's in terms of voltage. And again, driving force is kind of the force that's telling an ion to move one way or another across the membrane of the cell. So driving force is in terms of voltage. And so to find the total current moving across the membrane, we calculate the total of the conductance multiplied by the driving force for each of the different kinds of voltage activated ion channels, as well as leak channels, which I'll talk about in a minute. Because again, voltage times conductance equals current, so we are adding up all of the current terms to get total current. There are leak channels in the membrane that let some, mostly potassium, ions flow across the membrane always, so we need to account for that too. An equilibrium potential of the leak channels is going to be the voltage across the membrane at rest. And it's mostly potassium, which is why it's not fully like minus 80, but because it's only mostly potassium and there's some like leak sodium channels that are like preventing it from reaching fully like negative 80 millivolts. So yeah, so now we have this I total equation. And all these equations were determined from the Hodgkin and Huxley experiments, measuring from giant squid axons and using something called voltage clamp, which basically sets the voltage across the membrane of a neuron at a certain like set value that's not changing, so that the change in voltage over time, dV dt, is equal to 0. And the voltage clamp then measures the current needed to offset the incoming and outgoing currents to maintain that voltage and prevent the voltage from changing. For the leak conductance, G sub leak, because Hodgkin and Huxley knew that the equilibrium potential was negative 70 millivolts, they changed the voltage across the membrane by known amounts while measuring the current, and then they could solve for the leak conductance by dividing the leak current by the leak driving force. While there's also a capacitive current, I sub cap, where C sub M is the membrane capacitance, the capacitive current doesn't really matter for the Hodgkin and Huxley experiments, because the entire point of their experiments was to see what was needed to keep dV dt, change in voltage over time, equal to 0. And if dV dt equals 0, the capacitive current term will also be 0, as you can see. So threshold conditions for an action potential to happen are M equals 0.4, H equals 0.5, M cubed times H equals 0.032, and N equals 0.4. At this threshold point, even though the conductance for the potassium is greater than the conductance of the sodium, the driving force on the sodium is a magnitude of 100 millivolts, which is far stronger than the driving force on potassium of a magnitude of 40 millivolts. So if an action potential begins during the rising phase, within a half millisecond, M almost reaches 1, while H drops because some of the sodium channels get plugged, and then N rises as the potassium channels start to open. Then as the falling phase starts, H starts to drop as many more of the sodium channels get plugged up, and N rises. During the hyperpolarized refractory period, M decreases as the sodium channels close, N decreases as the potassium channels close, and H increases as the plug comes out of the sodium channels. So now that we've figured out the total current flow moving across the membrane, how many ions do you think flow across the membrane of a neuron during an action potential? We can actually estimate this. To approximate how many ions flow across the membrane of a neuron during an action potential, let's pretend the neuron is a sphere and find the volume of the neuron using the volume of the sphere formula in terms of meters cubed, and the surface area of the neuron using the surface area of a sphere formula in terms of meters squared. Let's assume that the neuron has a diameter of 20 micrometers, so a radius of 10 micrometers. The volume is going to be equal to 4/3 pi r cubed, which is approximately 4 times r cubed, which ends up being 4 times 10 to the negative 15 meters cubed for our neuron's volume. Our surface area is going to be 4 times pi r squared, which is approximately 12 times r squared, which, is approximately 10 times r squared. And that ends up being 10 to the negative 9 meters squared. The capacitance, the ability to hold charge per unit area of a biological membrane, is 10 to the negative 2 farads per meter squared. Farads are basically in terms of the amount of charge per volt, and the charge is measured in units of coulombs. So our neuron's surface area that we calculated up here, multiplied by the capacitance per unit area, will give us just the neuron's capacitance, which is going to be 10 to the negative 11 farads. Again, farads are in terms of coulombs per volt, so we can multiply our neuron's capacitance. We can multiply our neuron's capacitance by we can multiply our neuron's capacitance by the amount of voltage change observed during an action potential to find the coulombs of charge, which are going to be so our membrane needs 10 to the negative 11 coulombs of charge to change its voltage by 1 volt. And during an action potential, the voltage changes by approximately 100 millivolts or 0.1 volts. So that means we will end up needing 10 to the negative 12 coulombs of charge to flow across a membrane for an action potential. but how many ions is this? Well, since sodium and potassium ions each have a +1 charge, which is the same magnitude, though the opposite sign, as an electron's charge, we know that the number of potassium or sodium ions that make up 1 coulomb is going to be equal to the number of electrons that make up 1 coulomb. This number is 6 times 10 to the power 18. So we multiply that number with the coulombs that resulted from our multiplying the capacitance with the voltage. And this should give us an approximation of the number of ions that flow through the membrane, which is going to be 6 million ions. This means that 6 million sodium ions flow into the cell during the rising phase, and around 6 million potassium ions flow out during falling phase. Do you think this has a big impact on the cell? It's a lot of ions and the cell is really tiny. Well, we can see how many ions do we start with. Let's find the rest, let's take the rest concentration of the ions and convert it into ions per meters cubed, and then we can multiply the ion with per meter cubed with the volume of the neuron to find out how much impact this has. For sodium, the rest concentration is 15 millimolar, or 15 times 10 to the power -3 moles per liter. And moles per liter is a measure of concentration, how many particles there are in a specific volume. 1 mole is equal to 6 times 10 to the power 23 particles, and 1 liter is going to be 0.001 meters cubed. So the sodium concentration is going to be the 15 times 10 to the -3 moles per liter, multiplied by the number of particles per mole, multiplied by the liters in per, like how many meters cubed there are in a liter, which ends up giving you 9 times 10 to the power 24 ions per meters cubed. Now, from our earlier volume calculation, we found that the volume of our spherical neuron is going to be 4 times 10 to the -15 meters cubed. And so if we multiply that by the sodium concentration that we just found, then we end up getting 3.6 times 10 to the power 10 sodium ions. So the 6 million sodium ions flowing into the cell during an action potential really only change the amount of ions by like 0.017%, which isn't much of an impact because there are just so many sodium ions at in the resting concentration. Now, if you want, you can try this for potassium. Before an action potential, the concentration of potassium ions inside is 100 millimolars. So how much of an impact do you think the flood of potassium out of the cell has? Yeah, so that is it for this bonus lecture. Remember to turn in your science fiction story homework assignments to Canvas at the beginning of class on September 14th. I'm really excited to read them. And I hope you have a wonderful rest of your day. This, again, was material that I learned during my independent study, supervised by Dr. Brazier. And yeah, have a great week and goodbye.